program for LED blinking. Okay, using the Dragon 12 demo board. So what you have to do, first of all, you have to call all the register 9s12.h file, and then next you have to configure port B and port J as output, and then make sure your J1 must be ground, and then you will turn on all LEDs, and we need certain time to turn on all LEDs, so we need to go to subroutine delay, and then we will turn off and need the certain time also, and we have to go to the subroutine of delay, and we have to repeat. Okay, so the process is turn on in the certain time, and then turn off in the certain time, and then repeat. So that is the LED blinking operations. So in this program, you have to write the subroutine of the delay. So example instructions you use for subroutine of the delay, you want to call it, so you have to use JSR, jump to subroutine. And same as if you are required to write a program for LED running light. So LED running light, it will turn on one at a time in a certain time, and then proceed to the next and next LEDs. Okay, so you have to learn how to write a program execution time, and then how do you write the complete program? Okay, you can refer to the lab sheet, procedure 1, lab 5. Okay, so this instruction for LED blinking, and then we need the subroutine. So let's say our label D250 and other one is D250 milliseconds, so we have to find D250 ms. So it is here. So your program will looks like this one. Oops. Okay, so this is your complete program. Okay, so this is a main program, this one is a main program, this one is a subroutine program, and then subroutine program we have to write RTS to go back to the origin, means go back to the main program. If you don't put RTS, so it will end your program, so your LED will not repeat. Okay, now we proceed module 4, chapter 4 with program execution of time. So now we are not using the timer to program the delay, so we just use the program or instructions to make a delay. Why do we need execution of time? Before this, we learn LEDs. So how we want to program such blinking? So LED can blinking and then LED running light, so it needs times. So now we proceed to the program execution of time. Okay, so now we have to know crystal oscillator, E-clock and clock period. The HCS12 uses the E-clock as timing reference. So the keyword here is E-clock. So what is E-clock? The frequency of the E-clock is half of that of the crystal oscillator. So E-clock, the frequency is just half of the frequency crystal oscillator. And our board, we are using the Dragon 12 plus 2 board. So the frequency is 48 megahertz. That is the crystal oscillator frequency. Thus the E clock is half, so we get 24 megahertz. And hence its one clock period is 41.667 nanoseconds. So how did you get the one clock period? So we have frequency for E clock. So we have a formula 1 over T. Okay, and then you will get T equal to 1 over Fe. So 1 over 24 mega, then you will get 41.667 nanosecond. Okay, so what is the meaning of 1 clock period? 1 clock period is one clock cycle for the instruction to be execute. Not all the instruction execute with 1 clock cycle, so you can refer to the appendix A. Okay, so first how do we program with 1 millisecond delay? So we start with 1 millisecond delay. Why we need 1 millisecond delay? 1 millisecond delay we cannot see with our eyes because it is very fast. So it will be used for the 7 segment letter. Why do we need 1 millisecond? So we will look at later. Okay, so we start with this instruction. Okay, so we have load Y. So let's say we have load Y. Just let it be load Y. So now we don't know the value, and then we proceed with the decrease Y. So if you look at the appendix A, decrease Y takes only 1 cycle to be executed. And then we have branch not equal. Branch not equal. And then where we want to go, so we will go to again to the delay. So means we will repeat these instructions. Okay, so B and E is 3 cycle. So when we have 2 instructions with 1 and 3 cycles, so we have to total the cycle is 4 cycles. So 4 cycle. So 1 cycle we get 41.667 nanosecond, and 3 cycle we have 125 nanosecond, and 4 cycle we get 166.667 nanoseconds. So we don't complete yet to get 1 millisecond delay. So how we get 1 millisecond? How do we get? So you can use this formula. 1 millisecond equal to X 166.667 nanoseconds. So how many X you need? So you just divide 1 millisecond with 166.667 nanosecond, and then you will get about 16,000. So means the instruction of decrease Y and branch not equal, you have to repeat 16,000 times. So then you can get 1 millisecond. So that's why you put 6,000 here. So this is the basic of how do you get 1 millisecond delay. And then how do you want to make a 250 millisecond delay? So by using the 1 millisecond program, and then we have to repeat it 250 times. So how? Okay, so this is the basic. Okay, this one is the basic. We have 1 millisecond. So how do we repeat it until 250 times? So we have to use this instruction. Okay, so we just used a counter. Okay, to put the data 250 into the counter. So where is the counter? Counter is actually refer to the here. So it is actually the address of 1200. So we will put 250 decimal. So it will you have to convert to hexa. So it will save, it will keep inside the 1200 address of the memory. And then we decrease counter, so counter will become 249. And then not equal to 0, so it will repeat this one. So we will get another 2 millisecond. And then now decrease counter we have 248. And then repeat again, so we get 3 millisecond, and so on until we get 250 millisecond, and then it will return to another subroutine. Okay, and then how do you want to make the delay more than 250 millisecond? Okay, first, because of the value 250 here, maximum is just 255. So you can only get 255 milliseconds only. However, we have 6,000 here. 6,000 here, maximum is 65k plus because it is 16-bit. So you can change the 6,000 here. Okay, and otherwise you can add the cycles. For the cycle here you can add, so let's say before the decrease y and branch not equal, you put the NOP, no operation. So let's say NOP is 1 clock cycle and you put 2 NOP, so another 1 clock cycle, this one is 1 clock cycle, and the total one you get 6 cycle. So 6 cycle you multiply with 41.667 nanosecond, so the value will change. So you don't get 1 millisecond anymore, so it will increase. Okay, so that's all for program execution of time.